Just off the northeast coast of the United States lies Long Island Sound. It is a vital estuary bordered by a densely populated watershed, with over 9 million people living in the immediate area feeding into it. This map shows the dissolved oxygen content of the Sound's bottom waters in late summer 2013. In the black and dark gray areas near the western edge, dissolved oxygen drops below 2 milligrams per liter. This severe lack of oxygen is called hypoxia. When oxygen concentrations fall this low, aerobic aquatic life cannot breathe. Fish, crabs, and other organisms must flee the area or suffocate, creating massive biological dead zones. This scale of oxygen depletion stretches far beyond the Northeast. The Mississippi River watershed drains a massive portion of the North American continent, funneling continuous runoff straight into the Gulf of Mexico, triggering a dead zone that can span thousands of square miles. These expanding hypoxic regions represent a predictable, mathematical failure of biological systems, systematically devaluing coastal ecosystems and the regional economies built upon them. So, what specific human action strips oxygen from hundreds of square miles of ocean and estuary? The primary drivers of hypoxia are synthetic agricultural fertilizers and municipal sewage, introduced in volumes that overwhelm natural filtration. Aquatic ecosystems rely on elements like nitrogen and phosphorus. Normally, these act as limiting nutrients. They are the natural chemical bottlenecks that restrict how fast aquatic plants and algae can grow. When heavy agricultural and urban runoff dumps metric tons of these compounds into the water, that biological bottleneck is removed entirely. This sudden influx of life-sustaining nutrients triggers a fatal chain reaction known as cultural eutrophication, unbalancing the entire ecosystem until it inevitably collapses. This diagram outlines the exact sequence of events that drive cultural eutrophication. It begins with nutrient loading. Point source sewage discharge and non-point source agricultural runoff carry dense concentrations of nitrates and phosphates directly into the surface water. The immediate biological reaction is explosive. Without their natural nutrient limitations, the single-celled surface phytoplankton, commonly known as algae, multiply exponentially. This hyperconcentration of algae is called an algal bloom. The dense mat of organisms drastically increases water turbidity, turning the surface into an opaque shield. Because sunlight can no longer penetrate the murky water, benthic or bottom-dwelling plants are starved of light. Subsurface photosynthesis halts, and the underwater vegetation begins to die off. There is a common misconception that the thick algae at the surface are suffocating the fish by breathing all the oxygen. But these living algae are actively photosynthesizing. They actually produce oxygen. The turning point happens when the bloom rapidly exhausts its artificial nutrient supply. The algae experience a massive sudden die-off, and all that particulate organic matter rains down into the dark bottom waters. This is where the true consumers enter the picture. Naturally occurring aerobic bacteria in the benthic zone begin feeding on the massive pile of dead algae. As their food supply spikes, these new bacterial populations explode. To break down all this dead organic material, these decomposers require oxygen. This requirement is measured as biochemical oxygen demand, or BOD. In a stable ecosystem, oxygen demand is balanced.
But under eutrophic conditions, as billions of bacteria feed and respire, the biochemical oxygen demand spikes violently upward. The bacteria are consuming oxygen far faster than atmospheric mixing or photosynthesis can replace it. Consequently, the actual dissolved oxygen in the water plummets. Hypoxia is therefore a bottom-up failure. It is driven entirely by the cellular respiration of decomposing bacteria, which is ironically fueled by the overgrowth and death of the surface algae. Environmental collapses rarely result from a single isolated variable. They happen when multiple stressors collide. A massive compounding factor is thermal pollution, often caused by power plants that draw in cold water for normal operations and release hot coolant water back into adjacent streams or lakes. This introduces a strict physical chemistry problem. As water temperature increases, the physical capacity of the water to hold dissolved oxygen decreases. The water simply cannot retain as much gas. At the exact same time, there is a biological reality. Higher water temperatures cause the metabolic rates of fish and aquatic insects to spike.
Because their metabolism is running faster, they must consume more oxygen just to survive. This creates a lethal intersection. The environmental supply of dissolved oxygen falls just as the biological demand for it rises, inducing immediate physiological stress on the organisms. When the oxygen levels drop past a critical threshold, the ecosystem undergoes a rapid, localized collapse, resulting in massive fish kills. Adding thermal pollution to an already eutrophic lake accelerates the timeline. It squeezes the organisms from both the physical and biological sides, guaranteeing mass asphyxiation. We can now apply this mechanical understanding to the Long Island Sound map from 2013. Look at the western edge near New York City. The high population density generates an enormous volume of stormwater runoff and wastewater effluent, directly loading nitrates and phosphates into the estuary. Because this end of the sound has restricted geographical circulation, the water cannot easily flush these nutrients out to the open ocean. The point source inputs remain trapped, accelerating the algal growth cycle. These deep hypoxic zones represent the geographic footprint of massive benthic bacterial respiration, fueled by the accumulation of organic matter from the thick surface blooms. These regional dead zones are the strict mathematical consequence of concentrated anthropogenic nutrient inputs, meeting restricted natural water circulation. Trying to fix a hypoxic lake by pumping oxygen into the lower layers or applying chemical herbicides to kill the algae only treats the symptoms. It is an inefficient, temporary fix to a continuous structural failure. True remediation requires breaking the cascade at the point of input. That means strictly regulating the application of inorganic agricultural fertilizer in the surrounding watersheds. It requires upgrading municipal infrastructure, specifically by improving wastewater treatment facilities to actively strip nitrates and phosphates from human sewage before it reaches rivers. It also relies on natural infrastructure. Restoring coastal wetlands provides a massive biological buffer, naturally filtering agricultural runoff before nitrogen ever reaches the open water. Preserving these aquatic ecosystems and the regional economies that depend on them means treating the watershed as a strict chemical equation. The only way to stop the biological collapse at the bottom is to cut the human inputs at the top.